Okay, this lecture is going to be about value function approximation when the state space is very large that we cannot represent a value function exactly. So instead, we need to use some kind of function approximation. So here the idea is that we use function approximation in order to represent a value function. From supervised learning, you know how to do it. We talk about different types of function approximators like decision trees, linear function approximators, neural networks. We want to do similar things for RL. Okay, so as I said, in many real-world problems, the state action space is so large that we cannot represent quantities like value function or policy exactly. So I guess the important keyword here is exact. So just for example, if we have a state space is a subset of RD, and D being greater or equal than 1, then exact representation of an arbitrary function is going to be impossible on a computer. Even if function is, say, one-dimensional, if, for example, it is like this, arbitrary function on value function on R is difficult to represent, or if you want to represent it exactly, it is impossible because there are infinite number of different points on real line, uncountably infinite. So we can't represent it with a finite computer. And some other case that we want to use, the state space might be large, is that, well, it is not RD, but it is, and it's finite, but it's very large. So for example, we have millions or billions of states. So here, even though we may be able to store them on a computer, like millions we can store, billions we can, but maybe that's not the best way to do. And also it is, we want to have something that is a bit more computationally easier. So in these cases, we do some kind of function approximation. So we approximate the functions using a representation that is feasible to manipulate on a computer. So in some sense, we want to have a compact representation in the sense that it is not too large, not in mathematical terms. If we do this, this is called function approximation. So assume you know what it is. So I guess that's a level of definition of what function approximation is. So this is storage, of course, or representation is only part of the story. But function approximation is also important for generalization. Like when we do learning, which is what we want to do in reinforcement learning, we want to be able to generalize our experience to other regions of state space that we haven't exactly seen. And without function approximation, or function approximation allows us to do it. So generalization is another important reason we want to do function approximation. Okay, so function approximation is used in, or studied in many different fields. Of course, machine learning, statistics, also in kind of approximation theory in math, they study it, each of them with different emphasis. We do it also in reinforcement learning, and we do it in different ways. So in some cases, we want to approximate the value function. So we have v pi or v star, these are the goals, but we don't have them, we can't represent them exactly, so we use a function approximator v hat pi or v star hat as approximation for them. So sometimes we want to approximate the policy. So instead of pi star, which we cannot represent exactly if the state space or action space is large, we use an approximate version which is easy to be represented and manipulated on a computer. Sometimes we also approximate a model. So we have a true model, but we can't say represent it exactly. But so we learn it with an approximate model. So this one maybe is most relevant in the case of model-based reinforcement learning, which we are going to talk about at some point. This other one, policy approximation, I'm not going to talk about today, but probably next lecture. And the other one is value function approximation. This is the topic of today's lecture. And I continue this lecture on value function approximation next session. So that's it. So let's talk about different types of value function approximators. A kind of important class of value function approximators are linear function approximators, which are both simple for implement, simple to analyze, especially simple to analyze, but also general enough that we can talk about many different function approximators using a linear function approximation the way I'm going to define it. So how does it work? We choose a basis function the same way that we do in machine learning course, that there's a basis functions or feature, it's also called feature, phi, which would be a mapping from input space to some RP. Okay, I have it here. And then we define the value function, approximated value function, as the inner product of some weights and these features. So it would be phi transpose W, or in expanded form, it would be summation over phi I at x times Wi. I is the ith dimension of that feature vector, and I is going to be 1 to some number p, like 5, 10 million. So here there is this v hat, the approximated value function, is described by the choice of w. So we can write it also maybe in this more explicit form, that we have a w here. And by changing w, we can change the value function that we are approximating. Is this clear? Okay, so we can also talk about value function space. And in this case, which is the space of all possible value functions. So here, in this case of linear function approximation, what happens if we change w's to all possible vectors, d-dimensional vectors, we get different functions. The space of all functions would be called the value function space. And here in this particular case, what we have is that function space f would be in the form of functions from state to phi transpose x times w, when w belongs to Rd. In general, such an f is called value function space. And in this particular case, it's called linear function space. So we call it that way. So just important thing is that f, when I talk about f in the rest of this lecture and the rest of the course, it doesn't need to be a linear function space. It should be clear what the meaning, but here I'm talking about value function space in general. If if we are focusing on linear function spaces, then it should be clear from the context. So one thing I think that is important is that this linearity here is in parameters, in W, and not in state. So these are not space of linear functions in state variable, but just linear functions in W. So this means that we can represent functions that are nonlinear in states. Also, we can define the same thing for action value function. So for action value function, we can represent it by similar thing, with the difference that phi features would depend on both state and action. So that would be the difference. Okay, so just a very simple example of what a function approximation might look like. This is also a linear function, can be represented as a linear function approximator too. So suppose we have this blue function. So this blue function, and we want to represent it with some function approximation. A simple function approximation would be piecewise constant function, which is how it works. We divide the x-axis to parts with size epsilon. So we discretize state space. And then for each value of each of these partitions, we assign a number which represent the value of that function. So for example, we say that here, whatever the value is, that would be the vector I here. And this would be vector I plus 1, and so on and so forth. So here you see that I'm defining these constant functions by the functions on the left, the value of the blue function, the true function at the left side of that region. So these are kind of following it. And so this would be an approximation of this curve function by a piecewise constant. So we can define it also, we can denote this, or we can represent this as a linear function approximation if we choose the proper basis. So here we assume the domain is between -b to +b. We can define phi I to be an indicator function of this region, and you can check the indices, but essentially this would be like phi I. It would be 1 when x is in this region and 0 elsewhere. And then we can represent the value function as just a linear combination of these phi i's. So it's a linear function approximator. And for now, we can denote it with f of epsilon. This is not a notation that I'm going to use throughout the course, but at least for now. So, excuse me. So there are a few questions that we can ask when we choose a function approximator. One is that how accurate we can approximate value function v using this function approximator. The other question is that, well, how many parameters do we need in order to represent a function with certain accuracy? And the other is, what is the effect of this function approximation on the statistical estimation or on the learning part? Like if we have a very representative, or we have a function that can represent any other function very accurately, does it make learning easier or more difficult? Let's talk about this a little bit more in the kind of context of I use examples of these piecewise constant functions, but this is more general concept. So one is that the approximation quality depends on regularity or structure of the value function. So for example, if we allow that v to change arbitrary, then we cannot hope to have a good approximation. So what does it mean? So instead of, say, that function, let's have, instead of blue function, suppose I have a function that looks like that. So you see that if you have such a function, approximating it with a piecewise constant function is going to be more difficult. And even worse, maybe if we have a kind of I'm just drawing something that is crazy. Approximating this would not be possible because, say, for example, in this region, we have, for the red one, we have both positive numbers and negative numbers. So if, above that green curve line and below it. So it's difficult to find some middle ground that approximate that function in that region uniformly well. We could, of course, do better discretization. So, for example, if we choose a discretization that looks like, I don't know if I can, the partition is with higher resolution, I can capture a function that behaves less smoothly better. But that means that I need to have more regions there. Okay, so, and the functions that I drew were not really crazy. I mean, they look bad, but not the worst. So if the value function can be arbitrary, then we cannot hope to find any good approximation. If we add some kind of structure or regularity that make it continuous, like all the previous examples, we still can learn something if we have a higher resolution or higher discretization. If the function is, say Lipschitz, or its first derivative is bounded, so we know that the function cannot change much. If we add more structure on it, if we had, say, it's 5 times differentiable continuously, in that case, the function is going to be easier to approximate. So in general, this topic of, we can say that if a function has some form of regularity, and regularity here, for example, can be smoothness, but it can be other things. I mean, I use regularity in a non-precise way, or a very general way. We can say more. So for example, if V is a Lipschitz, then we can say that for any V that is a Lipschitz, we can find a V hat belonging to that's piecewise constant functions with the error that is bounded by L times epsilon. So if L is finite and epsilon is small enough, we can find a piecewise constant approximation that is accurate enough. So in previous examples that I had here, these functions are Lipschitz, the red one or the orange one, but the Lipschitz constant is going to be much larger than that nicer curve, the blue curve that is hidden right now. And that's why our approximation quality would be lower. So this amount of error, how much the best approximation we can have of a function is called the approximation error, or also bias in machine learning, which basically the error that how well we can approximate things. Okay, and so approximation error in general depends on many factors. One is that, well, the underlying function that we want to approximate. So the second item, like if the functions are somehow nice, then approximation error in general would be smaller. But also it depends on the type of function approximators that we are using for approximating a function. If we use a piecewise constant, or even worse, like if we use constant function, so if we have a function that looks like this, a constant function cannot approximate it very well. I mean, that's probably the best approximation. If we have piecewise constant, that makes a better approximation. We can use a piecewise linear approximation, which means that, say, let's try another color. So I still divide these regions. In each region, I get the best linear approximation. So this is the region, the best linear approximation in that region is this one. Here, the best linear approximation is this, maybe. So you see, this is much better than a piecewise constant approximation. And we can think about other function approximator classes, like higher degrees piecewise constant, higher degree polynomials, still piecewise. Or we can think about, say, neural network, a deep neural network. Each of them have different approximation capabilities. And that's essentially what this approximation error depends on. The function approximator and the function class that we want to approximate. Is there any questions so far? Okay, so the other thing that I want to talk about, okay, so there was a question. Yes, so the question is that can we use Fourier basis for approximation? Yes, definitely you can use it. And so Fourier basis, you can still represent the linear function approximation. You just choose the weights. And this is relatively recent. Surprising that nobody did it before, I think, 2008 or 9. But yes, it's good and it works well in some problems. Or wavelets, that's right. So we can use wavelets as another basis, which wavelets has nicer properties compared to Fourier basis because they can kind of localize in region that things are changing fast. So you need to have more number of bases in those regions versus, and in some region that everything is nice, you can have a fewer number of bases. So that's true. So these days, I guess most people, at least most people try to use deep neural network as a function approximator, which they have very nice performance and also nice properties, even though we don't know all the properties. They're not completely understood, as well as, say, simpler cases like just very simple case of, say, piecewise constant function. But they use it, but they can also use wavelets. I'm sure people have used wavelets. They definitely use Fourier basis for function spaces that don't have very high dimensions, which is actually this point that I'm going to talk about. So this is the curse of dimensionality in the number of parameters. So what does it mean? So here, just imagine the state space is a d-dimensional box. So it will be -1, +1, and it is d-dimensional. So in the previous image figure, it was 1, d was equal to 1. How many partitions do we need to represent such a function using this construction that I had, piecewise constant? I mean, it's easy to see it is order of 1 over epsilon to the power of d. So if it is x was 1-dimensional, so I divide it by epsilon, so a bounded region would require 1 over epsilon. If x was 2-dimensional, then each of them again is epsilon. So we have 1 over epsilon's boxes here or regions here, 1 over epsilon kind of partitions this way. So in total, we have 1 over epsilon squared. And for d-dimensional, we have 1 over 1 divided by epsilon to the power of d. So what's the problem with this? The problem is the number of regions grows very fast as dimension increases, right? So for example, if we partitioned each side, this region to 10 times, with kind of 10 different regions along each axis, so we will have 1 over epsilon, or then, okay, so maybe make it easier. Okay, so if it is, for this, okay, so if I choose epsilon to be equal to 0.2, I get, for this region, I get 1 over 0.2. The region is -1 to +1, so actually I have +2 here, so I get 10. So for d equal to 1, I have 10. That's fine. 2, I get 100. And if it's 10-dimensional, that would be a very large number. And notice that 10-dimensional problem, like a problem with 10-dimensional state space, is not actually very unusual or unheard of. Many real-world applications have dimensions that can easily be order of tens or even hundreds. And in some applications, like say, when we run a computer on Atari, say, the input is order of a few thousand dimension. I think Atari is like 7,000, 8,000 dimension, if I remember correctly. So that's very large. So we cannot hope to discretize the state space in this way. So this is one example of Kirchhoff dimensionality, that if you use a function approximator that is very simple, like this piecewise constant, we need to have a lot of regions in order to represent it. And soon as dimension increases, it becomes infeasible. And examples like, say, Fourier basis, if you want to do a Fourier basis, you can do it, but it has the same issue. Because if you have the same number of like 5 bases along each dimension, the number of total bases grows very fast in the same way. That's why usually those applications are successful if you have only a few dimensions, like 4 or 5 at most. Okay, there was a question. Okay, no, there was a question. Okay, so that's the Kirchhoff dimensionality. So the other part that I want to talk about is estimation error, which is essentially the question of if we want to learn a function using a finite number of data points, how much error comes because of this statistical part of this process of learning, that we have only a finite number of points, so we have some kind of error because of having finite number of data points. In general, I'm going to talk about it probably in next lecture. Yeah, definitely not today. But estimation error depends on some notion of complexity of the size of function space f. And quantifying this relationship requires some kind of further developments. But very roughly speaking, the behavior of this error would be order of square root of log of f divided by n. And n is the number of data points, and f, log of size of f, is a number of functions that we have in that function space. So this requires a little bit more work to be precise, or what exactly means, but this is the general behavior of this estimation error. So when the function space becomes very large, the effective number of elements of it or members of it would grow. And as a result, the estimation error also grows. And we can also see that the effect of dimension in this estimation error too. This is not obvious in this formulation, but you see that the size of f, or size of log of f, that has a dependence on dimension too. It would be dimension dependent. Of course, it depends on the type of function approximator, but for example, for piecewise linear or Fourier basis, that's the case. Okay, so maybe I'll just talk about this last slide and then try to finish it soon, or kind of, as opposed to last time, which was about 1 hour overtime. So we have different function approximators. As I mentioned, deep neural networks in general are commonly used ones these days. And people, when they apply it, they call it deep reinforcement learning. There are other approaches like there are other type of function spaces or function approximators. One is based on something called reproducing kernel Hilbert spaces. If you recall from your machine learning course, This is the same kernel that you talk about when you talk about support vector machines. So, and these were kind of the hype, not hype, but like the method of choice and a topic of a lot of research in like late 90s or most of 2000s, before deep neural networks become the hot topic of research. I mean, reproducing kernel Hilbert spaces, the topic is very old. It's like in mathematics, I think from the middle of 20th century. But in machine learning, it's much, in statistics and machine learning, it's more recent. I think in statistics started in 70s in methods called splines. So they used these reproducing kernel Hilbert spaces, or RKHS. And in machine learning, with the advent of support vector machines in the 90s, that became the thing. We can also use, we can use them in reinforcement learning. I guess that's the whole point. And they work fine. So decision trees and random forests, we can also use them. And we can have all sorts of local methods like smoothing kernels, which happens to be different from this type of kernels. K-nearest neighbors and a piecewise constant, piecewise linear models. So we can also use those. Okay, so I guess that's it. Next session, I'm going to talk about how we can actually use these function approximators in the context of reinforcement learning. So I start with first a setup where I assume that everything model is known, but we just can't represent the value function exactly. And I define some loss functions that if we minimize those loss functions, the result would be the good value function approximation. And then if we have those, going through the methods of learning-based methods when we don't know the model P or reward R is going to be relatively easy. We use either techniques from stochastic approximation that we had seen before, but kind of modified for value function approximation, or we use techniques similar to regression from supervised learning. And of course, there are other methods that I'm going to talk about a little bit too. I think that's all. Okay, so is there any question?